By expressing 1 in polar form and using Demois's theorem, find the solutions to z cubed equals 1 in polar form. So z cubed is equal to cis 2n pi, where n is an integer, as discussed in the previous example. We know that a real solution to z cubed, the only real solution, is z is equal to 1. As a complex number, that's cis 0, but of course, no matter how many times we go around the diagram, and no matter in which direction, we can get to that point if we go around a full rotation. So that's why it's 0 plus 2n pi. That means, using Demois's theorem, that z is equal to cis 2n pi divided by 3. So the n equals 0 situation, let's call this one z1, is cis 0. The n equals 1 situation, let's call that one z2. That's going to be cis 2 pi by 3. And then we have the n equals 2 situation. And that means that z would be cis 4 pi by 3. But remember, we normally give the argument in the range negative pi to pi. So that third solution would actually be cis negative 2 pi by 3. We're asked to convert these into exact Cartesian form, where clearly z1 is just 1. That's our real solution. z2 would be cos 2 pi by 3 plus I sine 2 pi by 3. So that's negative a half plus I root 3 on 2. z3 is cos negative 2 pi by 3 plus I sine negative 2 pi by 3, which is negative a half minus I root 3 over 2. Note that these two, the complex ones, are a conjugate pair. What is the sum of the three roots? Well, if we do 1 plus negative a half plus I root 3 on 2 plus negative a half minus I root 3 on 2, we can see that the 1 will cancel out with the negative a half and the negative a half. And because we had conjugates, the imaginary part of the two complex roots will cancel out. So we just get 0. And it might be obvious why that's the case when we plot these on the grid below. So one of them is here. One of them is going to be here. And the third one is going to be just here. And if you think of those as vectors, you can see why they all cancel out to give 0. And note, this is always the case, this symmetry with these roots of complex numbers.